Hello and welcome. I'd like to welcome everyone to our webinar, Boosting Performance Circuits in High Frequency Applications, where we'll be exploring the variables that impact circuit performance as well as ideas for improving design and functionality. This is the first webinar in a series about low-loss materials, and we'd love to get your feedback on other topics you'd like to see in our future webinars. I'm Linda Roleka, the Managing Director of the DuPont Silicon Valley Technology Center, and I'll be today's moderator. So a bit about us on the next slide. DuPont is a global leader in technology-based materials and solutions in specialty applications in electronics, transportation, construction, water, health and wellness, food, and worker safety. At the DuPont Silicon Valley Technology Center, we have 10 applications engineering labs equipped with a wide range of fabrication and characterization capabilities for rapid prototyping and testing. These are applicable to tech sectors in the area. Fabrication includes rigid and flexible circuitry, next-gen displays, and touch, thermal management, and printed electronics. Our characterization capabilities span RF and signal integrity, mechanical, electrical, thermal, optical, and reliability applications. In addition to the labs, our Innovation Center is a hub to learn more about our materials and is a place to engage with our design experts and our engineers. During the pandemic, we paused on on-site visits, but we do offer virtual tours and briefings. If you're interested or want to learn more about us, our contact information will be provided at the end of the webinar. So let's introduce our speakers for today. Our first speaker is Jeff Doubrava, a managing partner at Prismark Partners. Prismark is a provider of research into new and developing electronics technologies. Jeff will address low-loss materials in the consumer electronics, 5G for telecom, and automotive radar markets. We're honored to have him as our keynote today. Then following Mr. Doubrava will be one of our radio frequency engineers, Jonathan Weldon. He has more than 10 years of experience in the development of and delivery of novel circuit designs, materials, and fabrication processes with our RF applications investigative team. In this presentation, John will cover factors that affect signal loss performance, including materials, antenna design, and the environment. So a couple things before we start. With the exception of the presenters and myself, all the participants are on mute. If you have any questions, please use the QA function that's at the bottom of your screen, and we will address questions at the end. And if you have any technical issues, you can message the room moderators. Okay, and with that, I will pass it on to Mr. Doubrava.
This is Jeff Doubrava. I'm going to, over the next 20 minutes, walk us through the outlook for low-loss PCBs at both the application level and the laminates level. So as it says, low-loss laminate materials are used to fabricate a relatively narrow segment of printed circuit boards. But amongst the overall electronic materials market, it's actually one of the more interesting segments of the business, at least over the next 5 years. Low loss has been a market that's existed for probably 40 or 50 years, but it's definitely a market in transition. Historically, the market was driven by mill and aerospace, radar, high frequency communications, base stations back from 1G, analog base stations. Low loss laminates were used in antennas and power amplifiers. There have always been high frequency industrial applications. And then at least historically, there were some interesting consumer applications, radar detectors. Back in the day when we all had big satellite dishes in our backyard, they all used low-loss PCBs in the receiver segment of that. But the market today is really undergoing a rapid growth phase driven really by three segments. The first is the 5G transition. The movement to 5G is providing this boost over the next 4 or 5 years of strong growth, both installing new base stations and re-engineering the existing base stations. Radar, most particularly automotive radar, where radar modules are used in almost every implementation of ADAS. And our belief is that as the technology matures and the costs continue to come down, you'll see the use of radar in many other applications that have been enabled by that cost. And then finally, and this is probably most importantly from the flexible low loss materials segment, is these what we call the new consumer applications. The use of low loss materials in smartphones, watches, headsets, other applications that are going to receive some of the high frequency signals that 5G brings. Over the next 5 years, these three segments, the 5G transition, radar, and the new consumer, are going to account for about 90% of the growth in low loss materials are driven by those three applications. And I'll say a little bit more about each of these. Okay, so this is the Prismark view of the electronic systems production. So just to ground us, what this says that in 2020, there'll be about $2.05 trillion worth of electronic systems. In Prismark speak, a system is a fully functional electronic device. So a PC, a laptop, an automotive module is a system. Those boxes in blue are the most important segments for low loss materials and low loss PCBs. Mobile phones, wireless infrastructure, that's where the wireless base stations and the backhaul lives. Audiovisual, personal, those are the wearables, earbuds, things like that. Automotive is automotive radar. Mill and aerospace is still kind of the legacy radar and communications applications. So the first of these, and probably the most immediate, the one that's kind of in the rapid ramp phase right now, is the 5G transition. This is the fifth transition. So if you're old enough, you remember the first implementation of analog cellular. We went to 2G and then 2.5G, 3, 4, and now we're doing 5G. At least theoretically, 5G provides every user with the opportunity to download up to one gigabit per second. I don't know anybody who can actually use that much bandwidth, but realistically, 5G will give many people moderately high amounts of bandwidth all at the same time in the same place. Airports, sporting events, shopping malls, if we ever get to go back to those places again. And importantly is 5G will be implemented using both new and the most important here is millimeter wave and repurposed spectra. So it's going to reuse all the existing spectra for cellular communication and add a bunch of new spectra to that. And it's really driving developments at both the infrastructure level and at the level of user equipment. The infrastructure is really, it's the next phase of base station evolution. The user equipment is new. We never put low loss devices into user equipment historically. The increased bandwidth that 5G provides really comes from three different routes. The first is the fact that we use an improved algorithm. So the 5G algorithm is more efficient at using any amounts of available spectra. So you get more bits per second using the 5G algorithm than you did with the 4G algorithm. Secondly, and pretty importantly, is the fact that we're making a lot of new spectra available. Almost all legacy cellular communications happens at low band. So typically it's a gigahertz or less is low band. Mid band is greater than 1 up to about 6 gigahertz is the mid band. Almost all that spectra is new, and then all the millimeter wave spectra is new. And depending on where you're listening from today, in the US, all you hear about is millimeter wave. The rest of the world, a lot of it is mid band. But there's lots of new spectra, and that new spectra requires us to go install new equipment to take advantage of that. And the final point is the fact that in a really effective way of increasing bandwidth of any wireless network is to increase the number of cells. So you take and reduce the size of the cells and increase their number. You can automatically improve the amount of bandwidth you can deliver. And that's especially important for millimeter wave because the reach of millimeter wave signals is not very high. So you have to have a lot of small cells. But even at the low band and mid band, adding new small cells to any network improves its capacity. We're in the rapid ramp phase of the 5G transition. We counted the first true installations of 5G compatible equipment in late 2018, with the rapid ramp beginning in 2020 actually has been a really good year for the infrastructure business. It's one of the few segments of the electronic supply chain that was actually boosted by the pandemic, because the governments of the world, this is one of the levers they can turn to help prop up the manufacturing economy. So the 5G build out has not slowed down at all. It may have actually been accelerated a little bit by the pandemic. And the transition is really driving both brand new installations, a lot of them small cell installations, but also the upgrade of existing infrastructure equipment. The bad news is the fact that this is a 4 or 5 year transition, and this bump that's being provided by the 5G transition will really begin to peter out by about 2024. The business doesn't go away, it just stops growing as fast as it does right now. And we'll wait for the next transition, which is presumably 6G by 2028 or 2029. But this is one of the key drivers of low loss demand. On the rigid board side, really it's antennas and power amplifiers in base stations and wireless backhaul. And then the emerging use of high frequency materials in user equipment, antennas and connectors to those antennas. So this is our view of the base station equipment for both 5G, it's showed in the green bars, and 4G LTE in the blue bars before that. What I take from this slide is the fact that the build out follows exactly the same pattern as we saw with 4G and before that with 3G. But the transition, if anything, is a little bit faster with 5G, and the heights of the bars are higher because there are more users now than there were 10 years ago. So for any given network change, we need to install more equipment. And then you add on top of that, we're also are going to be installing a lot of small cells to provide infill in heavily populated areas. One of the other things that's important to note, especially from the low loss materials perspective, is that there's an evolution in terms of how the base stations are put together. Historically, and I mean 20 or 25 years ago, base stations were these big macro cells that sat on the tops of hills with discrete antennas and discrete amplifiers and transceivers at the base of the towers. We're now moving to these integrated designs, which people call antenna and radio all-in-ones, AAUs, depending on who you're talking to. But these are largely self-contained devices that have either moderate amounts of power, low power to moderately high amounts of power, and can, depending on the frequency, can handle up to several tens of kilometers, depending on where they're located. So that's what's happened on the macro cell side. On the other transition is the growth in small cells. So we're putting in lots of small cells in heavily populated areas to provide infill. So if you build a new housing development, you typically will not build new macro cells, but you'll put a lot of small cells in there to handle the people that transit through that neighborhood. So this is one of the first 5G compatible base stations that was installed in November of 2018. It was actually one of the first. I think this was done in Sacramento, California. It's an all-in-one, or depending on who you are, an all-in-one or an AAU. So it's a fully integrated base station design. It has the antennas, has the transceivers, has the baseband built into that. If we go to the next slide, if you look inside that device, this is actually a two-printed circuit board design. So the board on the left, the one that has the A's on it, that is the main printed circuit board that has the baseband as well as the power supplies and the control circuitry built into it. The second board, which is the center, and the one on the right, that's the radio board or the RF board. This is the mounting for the transceivers, and it also on the back side it actually has the antenna elements. Now, the reason this is important is the main PCB is almost certainly built out of either FR4 or a high-speed thermoset material. The board on the right, the RF board, the radio board, is almost certainly built out of PTFE or one of the alternative hydrocarbon low-loss materials, such as one of the Rogers materials. The second driver of the growth in low loss is radar, and most particularly, it's really automotive radar, because automotive radar is growing very quickly. Radar is a key element in essentially every implementation of ADAS along the continuum from completely manual to completely autonomous vehicles. Despite what some people say, we believe, and I think this is pretty well accepted, is that radar is not a competitor to other sensing technologies. Is actually complementary to other technologies. So you'll see camera modules, radar modules, LiDAR modules all coexisting because they provide different information streams, and they're actually positive to have multiple technologies in the same vehicle. And there'll be multiple modules per vehicle. There may be 5, 6, 7 radar modules per vehicle looking forwards, backwards, sideways, because eventually they'll be so cheap that you can do that. And as it says there, we're on the path to ubiquity. Right now, I'll show you the numbers in a couple of slides, but eventually every vehicle will have 4, 5, 6 radar modules per device, so that the ceiling for radar modules in automotive applications is 500 or 600 million modules, probably by the year 2030. This growth towards ubiquity really is enabled by price reductions. The first radar module, automotive radar module that Prismark ever took apart was in 2002. I think it cost us $5,000 for the module. He was in the top of the line Daimler materials. They called it adaptive cruise control at the time, but it was a radar-based system. Today, these are very inexpensive modules. They're cheap enough to be used in almost every newly designed car. The volume and the price reductions that come along with that volume will drive other applications, IoT, drones and robotics, eventually alternative human interface device, that's HID. So it's a way of sensing movements and finger positions. And the good news is every one of the antennas that we've ever seen for a radar module uses some sort of low loss material. People may vary in terms of which low loss material is used, but they all use some variety of a low loss material. So this is a slide we borrowed from Continental. So this is their view of the world. So if you think about autonomous driving, it's a continuum. We go from level 1, which is a completely manual automobile, no driver assistance whatsoever. Level 5 is fully autonomous vehicles. You essentially tell the vehicle where you want to go, close your eyes, and you'll arrive there when you get there. The bottom 3 boxes are Continental's view of how they'll get there. So what you see is even on only moderately automated vehicles, they're using 5 radar modules. When you get to fully automated vehicles, they're using 9 or 10 modules, radar modules per vehicle, despite the fact that they also have camera modules and LiDAR built into the vehicle at the same time. So it's complementary to camera modules. Radar is complementary to camera modules and to LiDAR both. So it's not either or, typically it's all 3. This is Prismark's forecast for electronics that it's used in ADAS applications. Just be aware that the heights of the bars are in billions of dollars. The numbers to the right of each of the bars are millions of units. So it's presenting both units as well as value. And there's pretty horrific price erosion with anything that gets used in the automotive supply chain. But what you'll see there is in 2019, there were 69 million radar modules used in the automotive market. Despite the fact that vehicle shipments are down by about 10% in 2020, the number of radar modules is almost flat, because this is a newly ramping technology being put into almost every newly designed car. And by 2024, I can't see the slide, but it's like 160 million modules by 2024. So it's ramping very quickly. And bear in mind that the ceiling, when we get to ubiquity, we're talking about 500 or 600 million radar modules. So there's a lot of room for this trend to continue to grow. Every automotive module we've ever taken apart has low loss materials built into them. They use either multiple printed circuit boards or they use a hybrid PCB. This is an ALPS 77 gigahertz radar module that uses multiple printed circuit boards, uses a conventional epoxy-based board for the digital side of the application, the power supply side of the application. And then down in the center picture, you can see that's the RF board, which actually contains both the transceiver as well as the antennas. This is a Bosch module. So this is an alternative 77 gigahertz radar module. They use a hybrid PCB. So they take a sheet of presumably PTFE based material and bond it to an epoxy based PCB, and they implement the different functionality, the digital on the one side, the RF on the other side. So every design uses one of these 2 approaches of either using 2 different boards connected together or use a hybrid design that contains both elements. As I mentioned, there are some legacy applications for low loss materials. Mil and aerospace, the market has not gone away, it's just not very fast growing. Military and aerospace, the military section of that is still growing at 2 or 3% a year. The commercial aerospace side will see a tremendous decline this year because of both the issues that happen with Boeing and the 737 MAX, as well as the decline in consumer travel and business travel. But long term, this is still a 3 or maybe a 4-year 4% growth business in a good year. Microwave backhaul is linked to cellular communication, but it doesn't scale at the same rate as does the number of base stations because it competes with fiber. But microwave backhaul uses low loss materials as well. And then these other consumer applications, they should be called the legacy consumer applications. They still exist. None of them are very big. None of them are fast growing, but they all use low loss materials such as PTFEs. The last segment is what we call the emerging or the new consumer application, and that's the use of low loss materials in smartphones, earbuds, wearables, and eventually lots of other high volume consumer devices. Historically, you never saw low loss materials in consumer devices. Any advanced PCB engineering efforts were really focused on density and packaging efficiency, not on pure electrical performance. So there's a lot of things that were developed driven by high volume consumer electronics like SLP, the use of rigid flex, but they weren't low loss focused. That really has begun to change, and the first design that we're aware of was done in 2012 by Apple. In the iPhone 5, they used an LCP-based flex circuit as a replacement for either a polyimide flex design or a piece of micro coax. I'll show you the design in a couple of slides. And today you see, moderately strong use of both LCP and modified polyimide in these applications where you have moderate to high frequency signals in a high volume consumer device. Neither one's as big as the traditional flex circuit materials or flex circuits business, but they're both growing faster than does the conventional business. Today, it's still a pretty small part of the overall flex market, about 6% overall, and used in a pretty narrow swath of applications, really mobile phones, smartwatches, earbuds, but there's good prospects for growth and expansion beyond those applications. That being said, there's still very little, that's a consultant's way of saying we don't know of anybody who uses rigid low loss materials in these consumer applications, but there's a fair amount of flexible materials being used today. So this is a teardown of the iPhone XS Max done about 2 years ago. And there are, I think, 21 pieces of flex in this phone, a lot of them used to connect modules into the main boards. There actually are 4 pieces of low loss flex in this design. There's 3 of them shown in this picture. The 2 that say antenna flex kind of at the 12 o'clock position, and then the one that says antenna flex at about the 4 o'clock position down below. These are LCP low loss flex designs that Apple was kind of the pioneer in prompting the use of LCP in a volume application. So the iPhone XS Max is the fourth from the right column. So you see there's 21 pieces of flex. 4 of them happen to be low loss pieces of flex. And what you also see is when Apple went to the iPhone 11 the next year, the number of pieces of LCP went down because they began to use modified polyimide, which is a easier to implement low loss material that has gone and stolen some of the share, some of the growth from LCPs. This is just another example of the use, again, by Apple of a low loss material. This is the Apple AirPods 2, and the bottom picture, the component labeled 3, that's actually the Bluetooth antenna that wraps around the battery used in the AirPod, and that's actually fabricated from LCP as well. So if we look now at the low loss laminates business, as I said in my introduction, low loss PCB laminates are some of the fastest growing electronic materials, not just the fastest growing PCB materials, but some of the fastest growing 165 electronic materials. And realistically, this is 2 distinct independent markets. There's the rigid market, which is historically divided into fluorinated materials, PTFEs, do very well in base stations, automotive radar, as well as hydrocarbon designs based on either polybutadiene, PPO, some at least proposed use of LCP. And I don't know that we know of any commercial use of LCP today. And the big applications for rigid low loss materials are 5G base stations and radar modules. That's the 2 big fast growing one. The other application is low loss flexible materials. And here we have LCP and modified polyimides. The choice of modified polyimide versus LCP really depends on the loss budget and the pain that's involved with using LCP. LCP is not particularly easy to make printed circuit boards out of. But the applications, the big applications for these low loss flexible materials are smartphones and wearables. And as it says there, the choice between these materials really depends on fitness for use. So, you're not going to use flexible LCP in an application in which you're going to build a multi-layer rigid board. Are you building a simple board, a complex board, building a flexible board, building a rigid board? The second issue is electrical performance. What is the acceptable loss in the design? That may limit the number of laminates that can actually live within that loss budget. And then the final one is total cost. And it's not just the cost of the materials, it's also how easy are they to put into the existing production process. What is the yield that you can expect in that production process? LCP has pretty good electrical properties, but it's not an easy material to use in production. So that's part of the reason that people have begun to use modified polyimide in those applications. Next slide. So this is my next to last slide, my last slide. So this is the overall printed circuit board laminates business. So this is all classes of laminates, rigid, flex, and all generations. So about $14 billion PCB laminates business, growing at almost 5% a year. The reason the growth rate is that high is because we used 19 as the base year. 19 was a relatively poor base year, so boost the growth rate. This is traditionally a 4% growth business. And then within that $14 billion are the two segments we've been talking about, the kind of the purple segment up at about 10 o'clock, and low loss flex, which is shown almost at 12 o'clock. So the low loss rigid, that's where the PPO, the PVD and the PTFE materials live, and low loss flex is where modified polyimide and LCP materials live. And they are some of the fastest growing PCB laminates are those low loss materials. I believe that is my last slide, and I would thank you for your attention, and I'd like to turn it over to Jonathan.
Thank you, Jeff, for the lead-in and the intro. I appreciate that. Great content. Hopefully I can follow suit and describe some of these materials in use. Let me go ahead and proceed here. Again, I'm Jonathan Weldon from DuPont. I'm an RF engineer by trade and not a chemist. So if you have chemical questions, we'll find somebody else to answer those. But I hope this is of interest to you, and I will do my best to describe low loss flex from a technical perspective. So I'll go ahead and push forward to kind of go to the overview here. The agenda is really, I'll say, slanted toward partnering with DuPont. And what I mean by that is viewing DuPont as more than just a material supplier. So as I go through the rest of this agenda and the slides, please think about any issues you might have in your design, your fabrication, and think about how maybe you would like to partner with DuPont to solve those challenges. And that can be anything from an insertion loss problem, a manufacturability issue, or even just how to design something and manufacture it combined with your system. So please keep that in mind. But as I go through the agenda, we'll be looking at flex materials and loss performance. So what I'll do is kind of go through a list of what materials are available and what you can sort of expect in terms of their high frequency performance. I'll go through sort of a use case of a transmission line and talk about design and characterization of that transmission line, and then how those flex materials and different loss values will play a role in your overall system performance. And then I'll go through a couple of other cases of something called crosshatch optimization. So looking at how to design a crosshatch for high frequency utilization. That's pretty much a hot topic across a lot of the flex industry. Crosshatches are very common to improve flexibility, but they do come with some challenges. And so I'll discuss those challenges and talk about how to sort of mitigate those and how to use it effectively and actually get a performance benefit from that. And then the last part, I'll talk about some antenna design and optimization and look at how environmental conditions like temperature and humidity will impact antenna performance. All right, so pushing forward, partnering with DuPont, and this is just a general overview, but what we can do for you beyond just help choose materials is provide support for design. We have a number of RF engineers, designers, and just a numerous collection of PCB experts from across the industry, both in flex and rigid. And so we can help you with designing circuit boards or designing even just segments of a current circuit board you are working on. So if you have a challenge, please bring that challenge to us. Let us help you solve those hard problems, and we'll do the best we can. Secondly, we have a lot of simulation capability that goes down to, I'll say, the RF side, but also thermal, mechanical, and numerous other software systems and even experts at simulating those, so we can help you verify the design you have or the design we come up with will work. Manufacturing, when it comes down to building that final part, we can pair you with a good fabricator partner. We can also help you build just a simple test vehicle to test out certain features on your final design to sort of mitigate some of that risk before you go to the first cut of the panel. And we can also just look at how to better improve things on your board for manufacturability. And then testing. That's always a challenge. Finding a good way to test an in-use sort of item can be tough, but we have a lot of capability in terms of designing those test features into a board, and then also testing those features for you as you move through the process of prototyping up to scale manufacturing. So again, please, as we go through this, think about how you might want to partner with DuPont, and if you have any major challenges, we would love to see them in the future. So Let me go first, kind of cover some of the building blocks. I put FR4 on here just as sort of a baseline. Everybody knows it's electrical performance. But just to kind of remind you, it's around 3 to 4 for the dielectric constant with a loss tangent a little bit over 0.01 to 0.02. And it's a pretty high DF value for anybody who's been looking at low loss materials, which I would typically classify as something around 0.005 or lower from the DF side. I've also included Pyralux FR. It's a very common flex material that people have used for quite a long time. It is an acrylic-based system, but as you can see, it has numbers that, although have a lower decay value than FR4, its dissipation factor is substantially higher than a typical low-loss material. So although it can be used for some designs below really 5 or 10 gigahertz, it's not suitable or really ideal for higher frequency applications where materials are going to really matter for you. Additionally, I'd like to bring your attention to the moisture uptake of that system. It can be a little high, which can play into the environmental stability I'll talk about a little bit later. So looking through the rest of these, we have a number of other, I'll say, high-performing products like Pyralux AP, HT, and TK, and I even included LCP on there because those are some of the most common or really the only major end-use flex products. Pyralux AP is typically an all polyimide clad, so there's a number of other products out there that would be similar to this. HT is an all polyimide bond film. I won't really talk too much about it, but it would be used in a multi-layer. And then TK is a Teflon Kapton composite. And as we look at some of these properties, you can see that they really trend around a dielectric constant of 3.2, maybe down to 2.5 for something that contains Teflon, and all really have typically a much better moisture uptake than Pyralux FR. Which is acrylic based, but one thing that really shines here is LCP with that extremely low moisture absorption of 0.04. But for everything else, you can see that loss performance is significantly better than FR4 as well. DF values well below 0.005 for all of those types of products. So I would say that any of those three are really, those four are suitable for high frequency applications. And I'll be talking about some of that as we go forward. So the next thing I would like to talk about is, putting some of those materials to use. And so for a use case, I'll be talking about primarily a microstrip. It's sort of the simplest transmission line structure we can build and test. And it's sort of the easiest one to understand and then break down. So what I've done is to construct a number of microstrip transmission lines and test them up to 40 gigahertz using a standard VNA. And what I'm showing here is sort of the performance breakdown of Pyralux TK versus AP versus LCP and even our AP product with different coppers. And the reason I wanted to show that is to, one, see how performance varies with dielectric properties, but also to see how performance varies with things other than dielectric properties. For instance, if you look at Pyralux AP with 2 different copper foils, you can see there's a pretty dramatic difference in performance there. And if we look at LCP as an example, with its ED foil in this particular case, it actually performs worse than the AP material does. And it's a little bit of a conundrum, right? We look back at the dielectric properties we just showed, and you can see that LCP with a lower dissipation factor and actually lower dielectric constant should in fact perform better. So what I'll do now is sort of walk through where the losses in these systems come from and hopefully show you how we can optimize performance based on your overall design. So the first thing to look at is dielectric loss. Actually, one of the easiest calculations we can do once you're able to measure accurately the dissipation factor and dielectric constant, you can simply back out the attenuation constant for your material and calculate a bulk loss over the distance your signal will propagate. A couple of key takeaways here is that dielectric loss is relatively, I'll say, substrate height independent. You can view it as sort of any composite structure bulk, and so as the field propagates through it, it is not unique to how thick or thin. It will vary slightly for a microstrip because the contribution of field that's in the air versus dielectric will change, but for something like a strip line or any other embedded structure, it will be independent of substrate height, which is very helpful because once we determine what our loss is based on frequency, we now kind of can tell where to manage our losses if they're a little too high. So looking at the plot here at the bottom, we can show that sort of the loss difference for, I'll say, an LCP versus an all polyimide like Pyralux AP. And we can see that the microstrip loss for LCP is about 0.096 dB per centimeter at 39 gigahertz versus about the same number for Pyralux AP. And you can see, although the loss tangents are similar, there is, I'll say, a great similarity there for other features as well. What is most important here is, if you think back to the loss numbers I showed you a moment ago, in terms of loss per centimeter, we're sitting at around minus 0.4 or 0.6 dB per centimeter at 40 gigahertz. So as we push and look at these values here, you can see we're not even hitting really 20% of our total loss coming from dielectric loss alone. So that said, let's dig a little bit deeper into different loss functions. And so if we look at the conductor loss, which is really the next part of this, it gets a little bit more complicated, because we're not just looking at a field traveling through a bulk dielectric with no conductivity. We're looking at field traveling through a confined, I'll say, current zone within a conductor that is modified by the frequency and skin depth. That's also modified by the geometries of the conductors. And we also have this roughness coefficient that comes up quite often if you're familiar with conductor roughness. And all of those things need to be managed to improve overall loss. But a key takeaway here is that your loss numbers at 39 gigahertz for both of these are sitting around 0.37 to 0.4 dB per centimeter. So thinking back again to the original plot where we had 0.5 or 0.6 dB per centimeter of total loss, we could see that pretty much 80% to 90% of our overall loss function comes from the conductor, including roughness. And so let's look a little bit more into that and see how we can improve it. So we talk about roughness. There's a number of things that come up. There's I'll say at least 3 or 4 solid models out there that people use. Models can help you get around 80% there, but it's always helpful to design and test. And I'll sort of show you why. So we've done a number of tests on different copper types, different roughnesses, different treatments of the nodule chemistry on the copper. And what we do see is that there's as much of a 2x spread in performance due to conductor type and roughness. And so what we're seeing in this plot here is really the spread that I was talking about. So you can see the top line is an 18 micron RA foil that's extremely smooth. In the bottom, we have a number of 18 micron ED foils that are also smooth, but also have a different nodule chemistry and a little bit different roughness. And right in the middle, we get kind of an intermingling. And so what this means is that by choosing foil, you can also modify by a pretty substantial amount the amount of loss you have in your system. So if, again, dielectric values alone aren't helping you get to the insertion loss numbers you need, choosing the proper foil can help. And DuPont can help you with that. Again, we have a pretty good bead on what foils are available, which will give you the best performance in what application based on frequency. There are variations in foil types based on frequency due to nodule chemistries and other things, and really help you make the right choice there to manage that overall loss budget you're working with. So having gone through the dielectric loss, conductor loss, and I know it's kind of a quick breeze through, let me talk a little bit about the composite view. And so I tried to pull it together into what I'll say is a pretty comprehensive window. But one thing to note here is that as I talk about conductor loss, it's a 50 to 100 micron wide transmission line. So relatively narrow, but common for a lot of flex circuits and even other sorts of constructions and telecom. But we can see if we start at the top left, those are the dielectric and conductor losses. If we look at values from 0.001 to 0.008 for dissipation factor, which are pretty common dissipation factors numbers for things from LCP all the way up through, I'll say, standard polyimide, we can see that it's, although a pretty broad window of performance in terms of its impact at 70 or even 80 gigahertz, when we're talking around 8, 10, 12, or even 20 gigahertz, it doesn't matter much. In fact, its contribution is well below the conductor contribution to total loss here. And the reason that's important is because if you start saying, oh, I'm using a material that has a loss number of 0.004, I got to get that down to 0.002, that 2x improvement in dissipation factor may not really buy you the performance you need. And so we'll look at other things like the conductor loss. That's the baseline performance number. Even if you were to build this circuit out of some sort of magic air substrate, this conductor loss would be there. And so your line width is really going to be the defining feature. And we can adjust that with design. We can help you find out if you've already hit the floor in terms of material entitlement. And you have to actually adjust the design to hit the performance numbers you need. But at the end of the day, changing materials to something with a lower DK value, like Pyralux TK, can help you increase that line width and decrease those losses even further. The bottom left plot here talks about conductivity and roughness. Those are a little bit odd to look at. Roughness is a little more obvious, meaning we have rough foil and we are attenuating field that's traveling through that interface between the dielectric and copper pretty heavily. So rougher copper will add higher levels of attenuation. But conductivity is that little red sliver there. And what you can see is that there's actually a difference in conductivity based on copper type. So if you have a heavily annealed RA foil, your conductivity might be better than something that is a little bit less pure or has a higher number of domains. And so although it isn't much in this sort of plot view, it can be upwards of 20 to 30% in certain applications. So that's something we can help manage as well if you're not hitting those performance numbers. And if we combine that, you can see that dielectric loss, conductor loss, roughness, and even conductivity of the copper give you this really substantial total loss window up here at the top, which is really the design window you have for a flex circuit. So again, if you're working on a design and you want help to try to find out where you are on here and how to move it a little bit closer up to the lowest possible loss you can have, happy to help you do that. And just as an example, if you look at really were to take 10 gigahertz off this plot, everything is almost completely dominated by conductor loss and by roughness. You can see that below 11 gigahertz as it's marked there, dissipation factor of 0.008 versus 0.001 is fairly negligible. Okay, so the next thing I'll talk about is test vehicles, and then I'll kind of circle into, I'll say crosshatch ground planes and then come back to this. I'm only showing our sort of example of a Pyralux test vehicle. We have many. We typically design numerous ones for different customers and different applications. So this is just one example, but we have a lot of experience optimizing test vehicles to get you a very pure measurement. This one, for instance, is the TRL-based test vehicle. It actually has crosshatch optimization on here as well. And we can add other mechanical features. And so we're happy to help you design some of these, build some, test them, characterize them for you, and get you data to really help out. And again, that's really all I want to get across here is that if you're having trouble finding numbers that will be representative of your performance and use, we can help you do that. So let me talk a little bit about crosshatch ground plane to pique your interest, and then hopefully you've been trying to use this with success, but if you haven't, we can help. A properly designed impedance match, I'll say transmission line with a crosshatch ground plane can give you 10% or more improved performance. However, it comes with a trade-off. You will have some adjustments to be made to your line widths, and you will have some modifications in terms of where the openings are placed versus the line. So one key point I'll say is that one, you don't get infinite bandwidth out of a crosshatch ground plane, and two, you have to actually design the ground plane from an engineering perspective. You can't just crosshatch a whole sheet of ground and place it on there and expect it to work. It is an engineered part when we're talking about high frequency. So let me push a little bit forward and show you that here real quick. If we revisit that test vehicle I showed a moment ago, what I've done is actually build different crosshatch types, different shapes, different geometries on top of the transmission line, very precisely registering them to the line themselves, building TRL calibration coupons along with it, and then kind of determining the overall change. And so in this particular case, you can see we really achieved a 10% or greater performance improvement below the cutoff frequency of the crosshatch. And the reason that's important is because currently, if you're using a best-in-class material like an LCP or an all-poly image structure, you're really within 5% of achieving entitlement level performance, meaning nothing more to the material will buy you a benefit. So design and these other sort of design considerations can give you twice as much as changing a material in many cases. And so again, encouraging you to work with DuPont, please, as you work through these problems, if you have a link budget issue, reach back out to us, let us know how we can help. We're happy to do some of this. And a lot of this can be done pretty quickly with 3D modeling and then a quick test vehicle run. So it's not usually a difficult challenge for us to tackle. Next thing I'll talk about is antenna design and modeling, something else we have the capability to do. This is just one example of doing an 8 gigahertz PFA, which is a planar inverted F antenna. Really, the design is fairly simple. We built it on some Pyralux AP, and I'll show you those results in a second. But we started by first modeling that and also measuring some material properties that we can add into it. And so we looked at the dielectric constant change of an all polyimide material over time in an 85-85 chamber. And you can see it's really a the dissipation factor is not here, but the decay changes by around 2%. Even at 85-85. And so it's a relatively minor change. You'll get a little bit of a higher move in the dissipation factor versus decay, but DF won't really modify your performance. Additionally, one thing to note here is I include CTE in this discussion because the movement of copper or the growth of those original antenna dimensions will modify the resonant frequency. And so that's something we want to keep in mind as well. So as we look at, as I kind of push forward, you'll see that moisture uptake and thermal will play a role in your overall antenna performance. And so what we did in this case was to take an AP material, build up that PFA as I showed earlier, and we can see that we have sort of a baseline case where we have AP sitting there as normal, and that's your solid, dotted yellow line. If we add humid air to it, so we don't have enough moisture yet to be absorbed into the dielectric, you can see that the resonance frequency shifts. And then as we start to absorb, it shifts even further. And then if we add a temperature change into that, you get a pretty dramatic shift down to the lower end. So again, why is that important? Environmental conditions can impact your overall performance, but understanding what environmental conditions to control can really help you improve your end result. And then putting that into practice, we built the PFA, and you can see I actually shorted the edge there across by cutting a little notch out. But we see a very similar change to what we predicted in our modeling. And overall, you can see that it's actually better than we anticipated, which is great. But good results, sort of at the end. And again, something we can help you do if you have a particular design and are worried about your environmental conditions. So again, summary and conclusion. Partnering with DuPont, please give us an opportunity to help you solve a hard problem if you have them. We'd love to hear from you, love to work with you. We can work with designers and provide targeted solutions and suggestions. So if you have just one small thing you're working on, we're happy to help with that. We can provide new designs and improvements and even model some existing designs and some of the concepts we come up with. We can provide test vehicles and help validate some of those results to really give you confidence. And again, work with fabricators to enhance manufacturability through the overall process. So that's all for me. I want to say thank you for your time, and I will turn it back over to Linda for questions and answers.
Hey, thank you, Jonathan. So I just want to, before we start the Q&A, we've got about 10 minutes for that. Want to let everyone know that this webinar is recorded, and both the webinar and the presentations will be posted on our website. We will send a link out to all of the participants. All right, so the first question will be for Jeff. So let me go through the Q&A. Jeff, what's your view on the split between small cells at 28 gigahertz and Wi-Fi 6 coverage? And which one will see the most deployment?
So good question. I'm not the right person to answer the question. So if they want to send me an email, I can put you in touch with our wireless guy. I'm a chemist, not an electrical engineer. So. All
right, and the next one that's around the market is, with the 5G implementation already in full swing, are the material sets of selection already a done deal, or are there still significant materials opportunities? And if so, where?
On the infrastructure side, it's pretty much baked in at this point. On the user equipment side, it's still a pretty dynamic market. So yeah, I think that, we're looking at maybe 4 more years of strong growth, and then it becomes relatively mature, not mature, but relatively mature. So I think a lot of the design work, a lot of the specifications have already been done.
All right, this one I believe will be for Jonathan. All right, you mentioned crosshatch optimization. Can you speak more about how you accurately predict impedance and performance?
Sure. So we've done a lot of work trying to understand crosshatch. We've built a number of test vehicles. That's where the data I showed came from. But most importantly, what we found is that you really only need to do a full 3D model on 1, maybe 2 crosshatch openings. And so what's been really effective has been building a design model that I can parameterize for different crosshatch geometries, so whether that be a diamond or a circle, and then run that optimization based on the material changes, stack up changes, and I've run in, I'll say, 99% accurate within 1 ohm of the overall, I'll say, impedance target, and then can get within, I'll say, 10% of what the overall, I'll say, performance will be from an insertion loss benefit standpoint. So running that model is actually relatively simple to do. Happy to help you build your own model if that's what you'd like. But once I kind of figured out that it was a single opening, it seemed to everything really started to click. So.
Okay, and then as a follow-up to that, modeling tools that you use for assisting high frequency design and simulation.
Sure. So we have numerous tools. So we try to keep basically all the tools that are out there, I'll say, on the shelf and in use by a number of our RF engineers. So we have things like HFSS, CST. I think we have Microwave Office as well. Basically, if it's out there and you're using it, even including ComSol and a few other ones, we've got it. So if you are having issues finding the right, I'll say, material properties to put into your database, please reach out to us and let us know. We can help you even do that, or look at your design and facilitate any way we can.
All right, this is another technical one. You discussed the line widths of up to 100 UM in your insertion loss section. Can I expect a dramatic change in performance if I have a wider line width?
You can. So typically what you'll see is that up to, I'll say around 150 micron wide line, you'll be sort of on this nonlinear curve where conductor loss will dominate. And then as you get above 150 microns or right at it, you'll start to hit parity with basically dielectric loss. And so once you get to this wider line width, you will be in almost a linear scenario where you increase your line width a little bit and you probably won't see much of a change in overall loss performance. And at that point, dielectric loss will probably dominate by 50, 60, or even 80% or more based on your frequency and application.
Okay, and then around Pyralux, the loss of the Pyralux and LCP with the same copper.
Ooh, that's a good question. When they're the same copper.
And Jonathan, as part of that one, what is LCP loss with rolled copper? So you could probably roll those all together.
Good question. So I will make a statement that LCP, everything else held constant, line width, or even adjusted line width for correct 50 ohm impedance. LCP will outperform all polyimide. That's not a problem if you hold the constant copper type. The major differences you'll see in performance for those are moisture uptake, so environmental functions make LCP a little bit better. But from the polyimide side, you do have improved flexibility. So if you do have a dynamic flex situation, it's going to be better. Additionally, you have easier manufacturing. It does work better and is more compatible with a number of adhesive systems, is better to laser and drill process, and typically makes a much more reliable system. One thing I sort of always take a stance on is to say that LCP, although viable for flex, is not suitable for high dynamic flex or I'll say high or narrow bend radius situations. It is a fragile material, although more flexible than something like a rigid board.
Okay, thank you. For Jeff, I believe this one would be for Jeff. So the high power consumption was one of the highlighted concerns of 5G. Has the material community heard about the ask and anything happening to address that from a material perspective other than low loss?
I don't know that I understand the question. The high power consumption?
Yeah, it was one of the highlighted concerns of 5G.
I don't know that that's the biggest concern we've heard. I'm not sure we've seen that raised. So no, I don't think so.
Okay.
So again, if somebody has a specific question, maybe they could reach out to me directly and we could figure out what maybe we just misunderstand the question.
Okay. And for Jonathan, how does ceramics play in the part of applications that you've mentioned?
So typically ceramics are going to be your high performance and high reliability systems, things like defense, mil aero. things like that, where there's going to need that stability and also that performance, because it does come with a cost premium when you start talking about ceramics. However, if we do look at the features, every plastic wishes it were a ceramic in some sense, right? So the moisture uptake is extremely low. Dissipation factor is typically lower than even an LCP in some instances. The decay values can be a little bit higher, but oftentimes can be made low as well. But the only real, I'll say, benefit that we have with an organic substrate is the ability to choose our conductor. When you're talking about a ceramic, you're firing a conductor on the surface, and so you do have some difference in performance based on not just purity, but also the actual formation of the structure of the copper, or I'll say, in most cases, silver or gold. So you will see a performance benefit in terms of reliability, probably insertion loss performance in certain scenarios based on let's say if you go with a very wide line, whereas in a flex circuit, you're typically very narrow. But they're going to be used in different ways for different things. And so happy to help you work through that if you're looking at a ceramic now and transitioning to a flex laminate. That would be interesting to see how that move goes. But if you're looking at flex and think you might need a ceramic, can certainly help you with that decision.
Okay, one for Jeff. The difference in the market categories of high speed and low loss.
There's increasingly overlap between those two segments, but to us, a high-speed laminate is used in a digital application. So the biggest application for high speed is servers and routers, and low loss is traditionally it's an RF application. So it's, you know, radar, wireless communications. But that being said, the high-speed laminates business, if you ask what's the most active area of development in the high-speed segment, it's reducing the loss. But there's still a pretty big gap between a low-loss laminate and even the lowest loss high-speed laminate.
And looking through more of the questions, does the roughness loss dominate the conductor loss? And what's the normal surface roughness?
Well, it can vary anywhere from really, I'll say 2+ microns for a standard rough foil down to, I'll say, tenths of a micron for very smooth foils. In some scenarios, it can be as much as 20% or more. I wouldn't say it dominates. It can be significantly more than dielectric loss for many flex materials, and even in some rigid boards if you're using sort of narrower line widths. So that said, base conductor loss, so sort of again that physical limit, is going to be more dominant in most cases. So if I had to stratify them, it would be base conductor loss, roughness, and then dielectric loss in most situations if you're using a high performance material already.
Okay, and I apologize. I was just watching the time and we just hit the top of the hour. We have many more questions that we haven't had time to answer. And so what we'll do is get those questions together along with the link to the webinar and the PowerPoint, and we'll email all of those Q&As to the participants. Our contact information is on the screen for those who would like to learn more about Prismark Partners, the DuPont materials and high frequency applications, or would like to visit the DuPont Silicon Valley Tech Center. There will be a survey right after the seminar, so please take a few minutes to answer the survey. We especially would like to know your other interest areas around low loss materials. So finally, I would like to thank Jeff Doubrava for sharing the market drivers and outlook in low loss materials in the consumer electronics, 5G, and automotive markets, and to Jonathan Weldon for sharing his technical expertise in materials and loss performance techniques and design. Thank you, everyone. And that concludes our webinar.